begin recording, and let's see, start the webinar now. And people are just starting to enter into the coming into the session now. Okay, so welcome everybody, and thank you for joining us for our MSc Electrical Power Systems Engineering webinar. And as you can see, today's topic is multi-energy systems and challenges for power systems. So my name is Craig Donaldson, and I am the course advisor, and I'm delighted to be joined by course director James Brooks and one of our academics, Martínez Ceseña, who will be running through a number of slides for us today. So just before I do hand over to James and Alex, I'd just like to say that you'll notice that when you're joining the session, that your cameras and microphones are off. And if you could keep it like that, that would be great. That would just help the panel concentrate on the slides as they're working through. But James and I and Alex would like to encourage you to send any questions you have through the chat feature of the webinar. And as we get towards the end of the session, I will pitch them to James and Alex and they can answer them for you. So that's it from me. I'd just like to also say thank you to those who watch us back as well. We don't want to miss you guys out. We do know that a lot of you do come back and watch what James has to say most of the time when we're doing the webinars. So thank you for that. And also you'll get my contact details later on so you can contact us post-session as well. So James, thanks very much for that, and I'll hand over to you now.
Yeah, excellent. Thanks, Craig. And yeah, welcome to everyone to this webinar and to those watching the recording as well. As I say, I'm the course director, so I'm responsible for looking after how the course is pulled together as a whole. But I'll just do a brief introduction to myself before handing over to Alex. So I'm a senior lecturer in electrical engineering, but I'm also the academic lead for pedagogy across all of science and engineering within the University of Manchester. So I have a real interest in improving the quality of teaching, the quality of education in those programs. And hopefully that comes through in the program that we put together here in electrical power systems engineering. And back when I did my PhD, I was looking at quantifying the risks in renewable power generation. So looking at what happens if you have a large number of non-dispatchable generators, things like wind turbines, and how you quantify and measure that risk as the penetration of those renewable resources changes. So that was me. And Alex, do you want to give an introduction to yourself?
Yes, my name is quite long. That's why I usually go for Alex. The whole thing is Eduardo Alejandro Martínez Ceseña, but Alex is easier. I'm an academic fellow at the University of Manchester, mostly working in terms of teaching in power system analysis and economics. But my work goes a bit beyond just power systems. I like to work with what it's called multi-energy systems, which is the combinations of multiple energy vectors. We're going to be talking about it later on. This is also called sometimes whole energy systems, although if you check the literature, the terms, they vary a bit. So the actual terminology has not been set of stone. In the context of this work, we're just basically talking about different vectors, mostly electricity, heat, and gas, but this can go into transport, hydrogen, and so on and so forth. And because of that, we don't see we don't normally see the network as simply power. We also see it as an integrated network that involves other things. And because we have so many moving parts, so many moving vectors, this becomes quite uncertain. And we're trying to assess it not only from the technical perspective, but also from the economic, which is basically what I'm going to be talking about. If we move on to the next slide, which is now about my presentation, I'm going to be talking about this whole idea of multi-energy systems, or whole energy systems, if you want to call them that way, a bit on what that actually means. So first of all, why do we care about these different energy vectors? If we look at the map of, this is a Sankey diagram, what it shows us is the different energy vectors that we use and the ones that we consume. So it's basically telling us We might take oil, we might use this oil to supply some generators. Those generators produce electricity and we consume electricity. So this is just depicting what we have. And we know that we have a lot of environmental challenges. We want to decarbonize our energy use. So first we need to see at what do we have? What is our energy use? And this is it. And the first idea was, okay, we know how to decarbonize electricity. We have renewable energy sources. So why don't we just electrify everything? What would happen if everything is running on renewables? And if we do that, then we would be saying, okay, if we want to electrify everything, we would be focusing just on the parts of this diagram that have electricity, which is that very small part shown there. So that gives you a bit of an idea of the problem. Do we really want to address our whole decarbonization challenges just by focusing on that little part? Does that make sense? If we move on to the next slide, we will get a bit of an understanding of the magnitude. So I'm not going to take all of the other parts of the diagram. Let's just focus on heat. So if we want to electrify heating, which is, let's say, with heat pumps or other devices, that means that we would have to be fitting what you see in the red line. James, if you can go into the animation, where we will be basically saying, if we want to electrify heating, we want to put everything in red into the blue line. So we will be trying to fit the heating into a system that was designed to cope with that small demand. In terms of heating, the electricity devices are much more efficient. So it wouldn't be exactly the same peak. So you would get only about 1/3 of the red line, but still is going to be higher than the blue line. What this is basically saying is that if we just say, let's electrify everything, let's just use renewables and focus on electricity, we would need to at least double the capacity of our current power system. And that is very expensive. And we're just talking about the costs. So let's see it from other perspectives. If we go into the next slide, let's think about, we already noticed that it would be quite expensive. We would need to oversize the whole system. But now let's look at it from the perspective of how flexible things are and how efficient. What do I mean with flexibility? With flexibility, I mean the number of options that we have at a given time to meet our needs. So if we have, let's begin with the current system. So in this current system, we have the electricity demand supplied with the electricity network, the heat demand meet with, in this case, a boiler, which is supplied by the gas network. So how flexible is this? How many options do we have to meet this demand? Well, if we want to meet the electricity, there is only one option. We can only use the electricity network in this case. If we want to meet our heat demand, there is only one option, the boiler. If we want to supply the boiler, there is only one option, that is the gas network. So we don't have much flexibility. We can only use one source. If any of this system is not sustainable, if any of these systems is expensive or fails, we don't really have much to do about it. And how efficient is this? This is going to depend on the technologies. So if we improve the electricity network, our electricity consumption would be more efficient, but not our heat consumption. To improve our heat consumption, we would need to improve the gas network. So we started thinking about, okay, we can have these different vectors, we can have these different networks, but as they're currently decoupled, they don't work that well. Now we start adding our renewable sources. Now we start electrifying everything. So in principle, we said, well, if we have renewables, this should be more renewable, more economic, or more reliable. That's why we're doing things like this. So, well, we see our system in this case with solar power. Is it more renewable? Yeah, you could say it is more renewable because we are using renewables. Is it more economic? Not necessarily, because now we depend a lot on the variations of, in this case, the sun. What happens at night? What happens if there's a cloud? We start having a lot of variations in our source. So that means we need to have something else to cope with these variations, something else that might not be cheap, like storage, like potentially fossil fuels that would need to cope with those variations. So it's renewable, but not necessarily economic. What about reliable? Well, before we said that if we needed to supply our heat demand, we wouldn't rely on the gas network. So if the gas network fails, then we're into troubles. What happens here? Well, if the electricity network fails and the solar is not very reliable on its own, then we lose everything. So if we rely solely on a single vector, our system actually becomes less reliable because we are simply having a single system. If that system fails, we lose everything. So even though this approach of just electrifying everything with renewables, relying purely on the electricity network, can be arguably more renewable, it's definitely not going to be cheap, and it's definitely not going to improve the quality of our service. So if we move on to the next slide and we start thinking of, instead of having our decoupled system on the left, we start trying to think of, okay, let's let's combine everything. Let's start using the different resources that we have. Let's continue using our gas network, electricity network, but in a way where we can switch, in a way that we perhaps can repurpose the gas network, let's say for hydrogen. Does this make more sense? Well, if you think about it, what are your options now? If you have the need for electricity, this can now be coming from the network, and now it can be coming from, in this case, a combined heat and power, CHP, which is a low carbon technology. So what you can do here is, if the electricity prices are too high, if you have uh, uh, too much carbon generation from electricity because of the sources, you can switch to a low carbon option, potentially cheaper. Then, well, I said that batteries can be quite expensive nowadays, but what happens if we store, instead of power, we store heat with the thermal energy storage, TES in this example? This is much cheaper, and we can use that to basically convert our electricity consumption into heating to use it later on. So we're basically now being able to use batteries if we want, but we can use other technologies. And what this perspective is basically telling you is that now you don't have to fully commit to electricity. You don't have to fully commit to gas or hydrogen. You can switch as you need. So this is much more flexible. If the electricity network fails, we go to the gas network. If there are too many emissions coming from a given vector, we switch to the other. So this is the perspective of the multi-energy systems. It's no longer that we have to tackle our issues with power. We have the flexibility to switch to whichever vector is more convenient in terms of economics, in terms of sustainability, in terms of reliability or resilience. Our system is less likely to crash as we have all these many options. And if we go into the next slide, the thing is, this is not easy to do. It's quite challenging actually, because over the last decades, we have been developing these systems as fully independent. Each of them have their own markets, their own actors planning and developing them. But we have realized that continuing to operate the system like that is not sustainable, not economic, not resilient. So we need to change our ways. And this is going to require a lot of research, a lot of work to bring together all these different silos in a way that they can communicate. And that is basically some of the work that we do here at the University of Manchester, trying to understand how to tackle the current challenges, and not focusing on the traditional approaches. It's not only about electricity anymore. We're looking at this from different perspectives, including different vectors, including economics, including the technical side, including reliability, and so on and so forth. And that is basically what I wanted to show with this presentation.
Thanks, Alex. That was a really good. I find it's such an important piece to think about. What are the external impacts, or what are the external factors that go on that are going to impact the electrical system? And if we just sort of move on, and I'll talk in the next few slides about what the actual electrical power systems engineering MSc looks like and the material you're taught. So while we don't focus hugely on multi-energy systems, I do think it's a very important thing to understand what those changes, what changes are coming and what's driving those changes, and thinking about how we're going to have to modify the system. But you know, when it comes down to it, there will still be voltage limits and power limits on a particular transformer, on a particular line, that have to be matched. We're still operating with the same power flows and load flows, but in a system that is a lot more complex and driven a lot harder. And that's why I think this is a hugely important area. Alex's work is a hugely important area to understand. So in terms of what we actually teach in electrical power systems engineering, we start off with a unit that really just introduces electrical energy systems and gives the fundamentals. We start going through some recaps of the basic mathematics and analysis that you'll need for the rest of the program. And then so I teach this unit. I try and get people thinking about things at a master's level. So going and doing independent research, going and discussing these big questions like, can we run a power system with renewable power alone? What does it mean for a system to run under a lower inertia? So we sort of have some good fun chatting about those sort of big open-ended questions and using that as a way of bringing in skills around researching and learning at a master's level. Once you've got that sort of fundamentals under your belt, you move on to the analysis of electrical energy and energy conversion systems. And here you're building up more of the fundamental analysis tools. You'll be looking at load flow, you'll be looking at faults, you'll be looking at analyzing power electronic devices and models in MATLAB and sort of hand calculating models as well. Once you've built up that sort of core analysis set of skills, you'll jump to one of the other units. They don't all happen in this order, and we constantly sort of make changes and improve things, but I'll run through them in one order. The next one is looking at, okay, what's in a substation? What is the physical components that we're talking about? What are they made of? What are the main design decisions that go into them? And here you'll be doing pieces of coursework like, okay, here is a particular specification. What piece of plant, what piece of equipment would meet that need? So it might be for a particular underground cable or overhead line. It might be a piece of switchgear or a transformer. And then the other piece of work you'll be doing in that is to say, okay, you've got this kit. How do we manage and monitor those assets over, let's say, a 40-year lifespan? What are we looking for within them? What indices and measurements and over what time periods do we look at those? So that's a very sort of physical view of the system. And then we move to a very mathematical, holistic view in operation and economics and say, well, a system is really run, many systems, by the finances. It is a mathematical optimization to say what is the best way to run this system from a financially efficient point of view, and how does this impact the operation? So I find it a really interesting link to say, yes, there's sort of mathematical optimization. There's also economic theory, but it also has to satisfy limits, like a generator will have a minimum and maximum amount of power that it can generate at any time. It will have limits on its ramp rates, its minimum and up and down times, and they will all constrain what is possible from the economics in terms of how we operate those systems. The next one is smart grids and sustainable energy systems. And this starts to touch on some of the work that Alex was talking about, to say, if we are seeing these changes, what's the impact and in this case, we focus more on distribution systems. What's the impact on a distribution system if a certain percentage of the houses install solar panels or electric vehicle, or buy electric vehicles and want them charged? How can we more smartly configure a network, a distribution network, to cope with those changes? We also start doing some literature review to really research the cutting edge of a particular topic. So it might be demand side management, customer incentives, something like that. Then there's a unit looking at the dynamics, quality of supply, and a bit on reliability and resilience as well. So rather than just assuming that everything's working how it should be, there will be fluctuations, there will be changes, there will be faults and problems, there will be harmonics. So how do we analyze systems from that perspective? And then if there are those issues on the network, how do we protect that to ensure that those problems don't propagate and spread to wider areas of the network? Finally, there's a unit that pulls all of that together into techniques for research and industry, where I ask you to come up with your own innovation, present it as a business case. So we're talking a lot about project management, teamwork. We're talking a lot about sort of innovations and independent research. And the idea there is to prepare you for some of the management and leadership work, and also some of the independent work that you may have to do on projects in work, and also you'll have to do in your dissertation. So those are the 8 taught units. They each last a fixed period of 10 weeks. 4 of those are entirely coursework based. 4 of those are exam based. At the moment, we're doing our exams online for obvious reasons, but they are normally run within a local exam centre, something like a British council, or we partner with a few different exam centres and universities in the UK as well. You can do up to 4 of those in a year, which means that to complete the taught period, it takes 2 years, and then you move on to the dissertation project, which is a big individual project, normally tied to something you're doing with the work that you're doing within your company. So particularly if your company sponsoring you, they get some research. You'll be paired with an academic who can sort of guide you through and provide support on that. Hopefully something useful for you and useful for your company. So that gives a minimum of 2.5 years to complete. Although many people don't take all 4 units every year, if they're taking big holidays, if they've got big work deadlines, we can shuffle things around so that maybe you only take 2 or 3 units a year and spread things out a bit more. In terms of what the units actually look like, this is one of the ones from Smart Grids. This one's broken up into 6 different sections. Each section then goes through and has a number of activities. So in this case, one of the activities, there's a video to watch, which goes through a particular worked example. In this case, saying how many electric vehicles could this system cope with, given the specification we've got here. But in addition to these videos, there'll be videos sort of giving an overview and explaining topics. There'll be practice problems that you work through yourself. There'll be discussion activities where you're interacting with other students. There's normally every other week, there'll be a live video conference where you can chat and have feedback with your tutor, someone like myself. And then there's Q&A sessions. There's the ability to email your tutors or to post questions in the discussion forum. We also provide access to IEEE Explore, so you have a huge wealth of academic research papers and access online to all of the books you'll need for the course as well. And we will ship out or give you access to a number of pieces of fairly standard software that you'll use to complete the courseworks, for example. And okay, so that's about the course. Why this course though? And Manchester's got quite a strong heritage in terms of its academic work. It's had 25 Nobel Prize winners either worked or studied here, including we've still got a number of current Nobel Prize winners working at the university. A large percentage of our research was world leading or internationally excellent at the last ref. We were the University of the Year for Graduate Employment. in the top 30 universities globally, and 6th best in the UK. And focusing down more on the actual electrical energy and power systems, power and energy division, this is probably one of the longest running power systems courses in the world. It was established in the early 60s, and we've had a long history of renowned researchers who and still have quite a large team that work in many different areas. It's nice to have experts in so many different pieces, from multi-energy systems, modeling of future power systems as a whole, people looking at individual components, aging of oils within transformers, high voltage testing, all sorts of different pieces. And it's nice to see them kind of come together to produce this. The other thing that I think is a real benefit is the people who come on the course from a wide range of employers. So we have, the large engineering consultancies, your Siemens and your ABB and your GE, but you've also got distribution and transmission system companies, system operators, you've got component manufacturers, you've got consultancies. So there's a nice wide range, and we get some really good discussions between people. In terms of what we need from you to be able to join the course or to be able to do well in the course, you need a 1st or 2-1 honours degree in something relevant like electrical engineering. It needs to be from a reputable institution. We also can factor in industry experience. I'll also be looking at the grades in the relevant taught units. So we're assuming a 2-1 level in power systems, in engineering, mathematics, in circuit analysis. So I'll be looking at your transcripts to look at those. And there is a route if you just narrowly miss out on those. So if you're very close to meeting this, but have got a lot of industry experience, there is a slightly different entry route where you'll take the first 2 units and we will assess you taking into account your CV and your grades in those first 2 units. The other thing we require is evidence of competency in English language as well. And you have to give us the money to join the course. But those fees can be spread out across the course and paid in installments. When you're actually on the course, you'll need to be spending roughly 15 hours a week for 40 weeks a year. And you've got to be able to attend the exam centres when things open back up. And you've got to have a computer fast enough to run the video conference tutorials and an internet fast enough to run that. And to be able to run IPSA, PowerWorld, PSCAD and MATLAB and the simulation software. So a Windows PC that can run those as well. And I think that's it from me. Please send through questions and we'll answer them either now or if you email them to Craig, we'll be able to answer them offline. But other than that, I will hand back to Craig.
Great, thanks, James, and thanks so much, Alex. It was such a fascinating webinar. It was really interesting. And the slides you can see there are my contact details. But by all means, please do get in touch to ask any questions you might have around your eligibility or the application process, and I can support you with that. And if not, I can get you in contact with James, who can obviously offer you some further guidance. I think a few questions have actually come through by the looks of it, James. I'll just take a look at the Q&A section now. I'm sure you can see them as well, James and Alex. Let me just see.
Yeah, I think the questions are mostly for Alex here. So, Alex, can you see the questions, or do you want me to read them out to you?
I see one comment.
Yeah. And then if you open up Q&A, there's a couple of questions in there as well.
Okay, yeah, I found it.
Yeah.
Okay. So the first one.
So why the move from gas boilers to air source heat pumps?
Mostly is because of the efficiency. So the efficiency of the heat pump is about 300% compared with 85% of a gas boiler. The other idea is that there is still a lot of focus on using electricity. So at least that is the current view, that air source heat pump or hybrid heat pumps are going to be the way to go. although if you check the future energy scenarios, the plans, especially for the UK, a lot of these plans also think that hydrogen is going to take over. So in addition to having these investments in heat pumps, most of the new buildings are also being district heating ready, meaning that the new constructions are meant to be designed with the assumption that something else supplying a district heating would work. And also the new boilers, the new devices are meant to operate with at least a 25% hydrogen blend. So the heat pumps is currently what seems to be working the best based on the plans, but there's are small preparations to switch into another direction as the technologies evolve.
Yeah, I think it's interesting to have efficiencies over 100%. And I suppose that's from an energy flow point of view, just the energy coming from the air outside, which we don't, isn't something that we would consider in terms of a fuel input. But yeah, it's fascinating that you can get such high efficiencies for air source and ground source heat pumps. Okay, and the second one, air source heat pumps consume 16 amps. I think that's a similar sort of question. It seems to have got rid of the gas source and moved to more consumption. And I think this is the point that Alex was trying to make before, that yes, we are taking away gas and moving things more into the electrical energy system with heat pumps, but the efficiencies are different. And I guess it's still a challenge to, if we go back to whichever slide it was, to fit the red into the blue. But maybe if you have an efficiency of 300%, that does certainly squash the red down a certain amount.
The issue here is that this is only one vector. If we factor in also electric vehicles, and now electric vehicles, you have slow charging, you have fast charging, rapid charging, and which have a massive demand. So the whole idea is that we are expecting too much for a single network, and too much very soon. So because we want to be in Manchester carbon neutral by 2038. So that's not so far in the future. And if we need to double or triple the capacity of the power network, that's not going to happen in that time frame.
I mean, to address this block here, which is transport coming from petroleum sources, if that was converted to electric vehicles, it would have to run through this red channel, and that's quite small compared. And again, the natural gas being the domestic part of natural gas, mostly going to heating and cooking sources here. If a large chunk of that was driven through the electrical network into this piece, you definitely see the power system being asked to do a lot more, even with the efficiencies, the increased efficiencies of air source heat pumps.
Yeah, so we need to do a lot of work on the power network, definitely. But at least on the short term, it's not going to be enough. So perhaps in 23 years, multi-energy systems won't be as appealing once we modernize the power sector to be as powerful as we need it to be. But at least in the short term, we would still need to rely on the other infrastructure that we already have.
Yeah. And I think one interesting thing that you don't see from this chart is the variability and flexibility required. You touched on it with the solar panels. What if it's a cloudy day? A lot of the resources that we're looking for in terms of renewable resources, you don't have that same ability to schedule or dispatch them in the way that you can with the traditional one. There is a variability there. Okay, let's have a look. What was the comment? Balancing the power system would require legislation of every single tiny power consumption to be constantly monitored and having a system to balance it out. Is that invading people's lives and communities are not looking forward to it? Yeah, it's an interesting discussion. If some of the kind of useful spaces for smart devices would be heating, space heating and cooling, so fridges and heaters, but it would also be electric vehicles. And I guess thinking through, just even as an end user, what sort of incentive would you need to sign up to a scheme that your battery in your electric vehicle was to be used to balance out the system, the power system when needed. And there would be certain downsides to that in terms of the life cycle of the battery and in terms of how much charge the battery would have when you come to use it. And I think that's another thing to look at in terms of the human aspect, in terms of how do you incentivize people, or how do you say, you know, all fridges must have a smart device monitoring it and are able to just turn off that compressor pump for a short period of time when we really, it would be very useful. But getting people to sign up to that is a hard thing. We do talk a little bit about that in the smart grids unit. There's some of the papers that we link to that discuss those challenges.
Yeah, it's definitely a big challenge. We do have some work, at least in some of the lecture, we do mention a bit how this would play in real life. Although the moment you start going into people behavior, legislation, markets, you start working a bit more on the interface between power engineering and other areas. So when you work a bit into markets, that is slightly related, but there is a specific variation of markets called transactive markets, which are the ones that focus on privacy issues. So it's the whole idea of you're not really seeing the customer's data, but seeing their aggregated response and how to send signals for them to respond. But this is very, very preliminary work so far, and it's not very reliable. And the moment you need to rely on these sources to support the system, and without that it can crash, then it's still a bit too risky to rely on those mechanisms until they become a bit more mature. Here you would also find things like blockchain, which is to allow this type of multiple interactions in a distributed fashion.
Yeah, we've got one of the MSc students on the course actually has just started a project, the dissertation project, looking at blockchain within power system. It's an interesting topic. Okay, I think if I skip back to the end slide, if anyone does have any further questions, because I think we're reaching the end of time, our time now, please send it through to the email address you see here, and Craig or one of his colleagues will be able to answer it, and if necessary forward it on to myself or Alex or whoever's in the best position to answer it if he's not able to. And I think just to say thank you to everyone for watching this, and yeah, let us know if you want to find out more.
Thanks, James. Thanks, Alex.
Thank you.
Thanks, everyone.